Okay, so yesterday I have sent you an email and the information about the talk that will be given tomorrow by Alkan Kabakçıoğlu. He's going to talk about, well, there's this one half of the Nobel Prize that's awarded this year. It's a work on spin glasses. So he's going to talk about this. In any case, I hope that he can simplify it as much as possible. I know that the topic is very complicated. Even I don't understand it because I have also somewhat worked on this topic when I was like at the start of my PhD. But in any case, I mean, I don't know much about the essential thing which is awarded by the Nobel Prize, actually. But in any case, the prize is about the complexity. There are some physical systems where the dynamics is actually extremely complex, but usually you're not interested in this detailed dynamics, but the overall and usually long time behavior. So the other half of the prize is given to some studies on the climate change, basically. So then there are these two other people who have done some work on the relationship between the climate and weather, basically. But again, I don't know what the relationship, I don't know what they have done. And I don't know if Alkan is going to say something about this, the other half as well, right? In any case, I suggest that you go and listen, and I'm sure that there will be things that you won't understand, but I'm also sure that there are things that I won't understand. But in these kind of talks, of course, I think the most important thing is that you actually gain something, whatever it is. It might be very small, it might be large, but you always gain something, okay? So as a result, it's just a suggestion. Okay, so that's just after our class on Thursday, our second class on Thursday. So it's like the third hour, which is announced, within the third hour, which is announced, right? In any case, today and this week, actually, I'm going to talk about basically quantities, the physical quantities. Quantities like, I don't know, let's say it like the 0.43 meters, for example. And there are some, I mean, it's just an example, obviously. There are some, I mean, this is a number. And we know that the mathematicians also deal with the numbers, but the numbers that the physicists use are actually somewhat different than the numbers that the mathematicians have developed, right? So basically, we all use the mathematics, obviously, but the numbers that we are going to see used in expressing quantities is actually somewhat has some additional features on top of the mathematical numbers. So the first thing is that, well, all of them have a dimension, right? This is the type of the quantity. It's actually quite hard to express what a dimension is. But when we see the examples, we are going to actually understand it better. So this is a quantity with the dimensions of length, basically. We write the dimension with this notation, with a square brace, and then write down the quantity in there, right? The dimension of the quantity. And with each dimension, there usually comes a set of units, basically. So in this case, the unit is the meters, right? Okay. So there is another thing in here. Let me also show it like that, okay? And there's another thing in here. Let me show it like this. This has some kind of uncertainty in it. I mean, all the numbers that you have seen in mathematics courses, they are precise, extremely precise. It is pi, for example. You know that, I mean, it has some infinitely many digits, but all of them are have some definite values, or things like 1/2 and square root of 2 and things like that, right? They are extremely precise. They are certain numbers, but usually when we are, especially when we express them as a result of measurement, it always contains an uncertainty there, right? That's also a common feature of all of these numbers. There's one last thing in here. So I'm going to talk all of them, actually, talk about all of them. This is a scalar. All right. This is actually a mathematical property. The scalars are just the numbers. And then there are these vector quantities that I'm going to also talk about within this week, within these 4 hours. Said, I mean, there's actually a well-defined mathematical theory behind that, right? So I'll also be talking about these. So let me actually add in here, these comments in here. So I'm going to talk about dimension. So there's something called dimensional analysis. I'm going to talk about that. This is actually a very nice thing. We don't usually teach this to students, but I mean, every physicist should know about this, because in some certain cases, when you cannot derive a formula, you can use this thing to guess what the formula might look like, right? That's actually very powerful. And I think I'm going to give some examples of it. But the essential idea is that in a formula, the units of all the quantities must be consistent with each other. So that's the essential idea. In dimensional analysis, we are using this idea in a systematic way to deduce the form of a formula, right? That's essentially what it is. But this is not really about units, but it's about the dimensions. So the units is something else. So I'm going to talk about the units. So it's going to be a very short talk. So I'm going to talk about the SI unit system. I'm going to talk about the uncertainty and the precision and things like that. So precision and yeah, I'm not going to talk about this uncertainty. But I might give an example about the why these kind of quantities might have some uncertainties. And of course, on this topic, the type of the quantity, I'll be talking about the vectors, not vectors versus scalars, but I'll be talking about the vector algebra. So we are going to spend some time on this. This is something that I actually explain separately. If you look at the textbook, the vector algebra is explained, but it's explained in like pieces. Some part is in the 2nd chapter and some part is in the, I don't know, the 7th chapter and whatever, 6th chapter. I'm not going to do this. So I'm going to explain everything, the whole algebra of vectors at the beginning, and later we are going to use them one by one. All right. So I think I'm also going to assign a homework on vector algebra. There are actually at least two quizzes, but so these are very simple quizzes. But I will also give a homework about the vector algebra, right? So this is something that you have to start using at some point. Okay. So let's then talk about these dimensions in here. All right. Again, if you have any questions, then either chat with me or you can just start speaking. The problem with dimensions is that I cannot describe it in a precise way. So I cannot give a dictionary definition of what dimension is. I mean, we're talking about these physical dimensions, all right? So dimensions of quantities, not the dimensions of space and things like that. So that's something else, all right? So we are using the same word to express a different concept, okay? So let me just say it like this. There are three base dimensions in mechanics, right? In mechanics, we use these three dimensions. So the first one is the length. And the second one is time. And the third one is mass. So if we just think about all the possible quantities that we meet when we are doing mechanics, all of them are basically somewhat derived from these. So these are base dimensions. And then let's say that there are many derived dimensions. So velocity, for example, is a type of quantity. It has the dimension of, length divided by time. Okay, so the acceleration is length divided by time squared. So let's just skip this. So energy, for example, is mass multiplied with length squared divided by time squared, right? So there's a force which is mass times length divided by time squared and so on, right? So these are derived dimensions. So, I mean, everything else is basically explained. Sorry about this. So, I mean, the dimensions are derived. So as a result, this has some consequences for the units as well. In any case, so if we talk about the units, I'll be basically using the SI unit system in here. So in any case, let me just say it like this. So there's some kind of a counterpart of all of these in the for the units. So let's say it like this. So for example, in SI unit system, we are using meters to express things with the dimensions of length, and seconds for expressing quantities with the dimensions of time, and kilograms for the mass dimension, right? And so as a result, we then define the units for the other derived quantities by using the same relationships, basically. So the meters per second would be used for velocity and whatever. So it's kilogram meters per second squared will be used for energy. And this has a special name, and joule, right? So in any case, you might think that the units is the same thing as the dimensions. Well, it isn't, because I can use different units to express the same thing. So for example, even in SI, for example, there's a centimeter unit and the kilogram unit and things like that. Or there are non-SI units like, I don't know, let's say inches, right? Yeah, let me say inches, miles, the British units, and I don't know, the Artian, and I think there are some units that is used by Turkish people at one time, but I don't know what the list is, right? So there are these things, Karish and whatever, things like that. Okay, so I don't know. I don't think that they are standardized, but these are actually kind of standardized because they are defined now with respect to these SI units. Okay. So first, let's just talk about the units, and then I'm going to pass back to the dimensions. Okay. So you can kind of see that the dimension is basically the general idea of the type of the quantity. But for the same type of quantity, I can, sorry about this, this is not kilograms. This is kilometers, sorry. I can use different units for the same dimension. So for the same quantity with the same dimension. So different units can be used, but it has the same dimension, right? So therefore, there's some kind of a distinction between these two concepts, okay? So we have to understand it like that. So as a result, without defining what the dimension is, I can actually explain it like this, okay? So let me first complete this thing. So these are only the quantity, the dimensions used in mechanics, but in other branches of physics, there are some other, let's say, base dimensions. So let me write it down like that. So there are these other base dimensions. Let's say in physics, the most important one of them is the charge. And the unit is Coulomb. So we are in the next semester, we are going to start using that. So therefore, in electromagnetism, there will be 4 base units, basically, and everything else would be defined with this. And then there are these additional things like the temperature. There's this mole thing. It's basically a quantity or the number of things. The mole unit is defined, and there's also some kind of a unit for the brightness of light, but just forget about them, right? Even forget about temperature. The temperature is essentially, well, it's basically related to some quantity that has the dimensions of energy. So there's some kind of a conversion factor between them. So that's also not, it's not a serious dimension, basically. So there are actually 4 possible dimensions that we commonly use if we take things seriously. But in practice, of course, when people are using these units, they are using these 7 base units in SI. Yeah, these are all base dimensions, right? Candela is the unit for the this visible brightness of light. But I don't think that there should be a unit for that. There can be a unit for it, but I mean, it cannot be defined in a precise way, I believe. In any case, so units. So the SI is basically, I mean, the French initiated this, actually. After the French Revolution, the Frenchmen have these crazy ideas about revolutionizing everything, including the science. So as a result, they came up with this idea of actually defining the units in a scientific manner and whatever. So therefore, they started defining these. So that they, for example, defined the meter unit based on the size of the Earth, for example, and whatever. So as a result, they actually tried to define everything in a scientific manner. So therefore, they started some kind of an well, this institution, and then at some point they wanted to make these to be international. So this is the, I need to say that this is the metric system. Metric system essentially uses the multiples of 10 to express all the other units. So centimeters, for example, is like 100th of a meter, for example. So this is basically done to simplify all the calculations. In any case, I think in 1860s or something like that, there was the first meter convention, 1860 something, I don't know. It's the meter convention. It's an international agreement signed by about 20 countries. Ottoman Empire is one of them, actually. So somehow they have established this institution in there and charged the institution with actually developing and maintaining these units. So their job is to define these units and somehow help other people to copy the units so that they can measure things in a convenient way. So over time, their definitions have changed. And I think the last definition, I'm sorry, it's not the, I think, but I'm not precisely sure if there's any additional definition after that point. So this is about 3 years ago, 2 or 3 years ago, where they started using these fundamental constants to actually measure things. So yeah, I don't know much about this. So it's 1869. Thank you very much. Okay. So in any case, so in science, therefore, we try to use this metric system. A lot of countries have passed to the metric system, so a lot of countries are using. There are only a few exceptions. United States is one of them. So they are still using the British system. Even the British doesn't use the British system anymore, but somehow they are stuck with it and they cannot change it. They want to change it, but they cannot. But in any case, so in daily life as well, this is used a lot. So there are only a few exceptions. Like if you want to measure the size of a monitor, we are still using the inches. But unfortunately, there are these kind of artifacts. But in any case, what's important in here, in scientific work, we should always use the SI units. So there are these prefixes that we use a lot, right? We know, for example, kilo means 10 to the 3. And then there are these other things like mega and giga. You have to learn some of the basic ones, right? So giga is 10 to the 9, and then comes tera, 10 to the 12. After that, I think it comes, exa comes, but I'm not really sure about this. So that's the part that I actually have ignorance, let's say, right? So when we start using exabytes of memory, then I will also learn that part as well. In any case, on the small part, we have milli. Again, this is something that you already know. We have micro as 10 to the minus 6. So the medical, the doctors cannot use this on their report cards. And so as a result, they are using this U symbol. So I don't know, it's like instead of micromole, they are using U mole or something like that, right? And after that, it comes nano. So I think after this, at this point, some of you will get confused, but just try to remember it like this. In the old times, in 60s and 70s, there was something called microtechnology, right? I think prior that there was a special name given to that technology, but I forgot the precise wording that they had used. In any case, microtechnology means that they are producing chips and things like that with the feature sizes of the order of micrometers, right? Micrometers. So micrometer is like 1,000th of a millimeter. It's basically the size of a cell in a way, or the size of the human hair, for example, is about 10 micrometers probably. In any case, it is that small, but still it is relatable. Nano is the next level in here. So it's basically 1,000th of a micrometer. So nowadays, people have passed the microtechnology. Now we are using nanotechnology, right? So nanotechnology basically talks about feature sizes of the order of nanometers. But in any case, I mean, this is a prefix that we use for all the other units as well. So there are things like nanofarads and I don't know, nanograms, sometimes for the mass of small particles, for example. small molecules, we can use these kind of units as well. Okay. So then it goes on. There is a pico. Unfortunately, there won't be any pico technology because there's nothing of that size. And there's femto. Femto is 10 to the minus 15. And I don't know what comes next. There's a yocto and zeto or something like that that follows this list. I think the next one is just forget about it. Okay, so I mean, with time, after using these kind of prefixes many times, you start comfortable with these. Otherwise, I'm sure that you're going to have difficulty remembering which one is which. So in the homeworks, for example, I'm going to remind you these. Okay, so in SI system, therefore, there are these base units. Okay, so after these base dimensions, so it is meter second kilogram. Unfortunately, the base unit for the mass is not gram, but it's kilogram. But yeah, atto. Yes, thank you very much. Atto is after the one comes after femto. Thank you. There's this coulombs. And for the temperature, we have Kelvin. For quantities, it is moles. And for the visible brightness, it is candela, right? But as I said, the others are not that important. So these are the important ones. And we have all the derived units as well, right? So there are these derived units. Oh, sorry about that. So it's joules, which is kilogram meters per second squared. And we can use the prefixes for these kind of things as well. So it's the millijoule, microjoule, kilojoule, or whatever. Sometimes in this course, I also use these kind of things. Okay, so instead of using very large numbers or very small numbers, I may use these units with prefixes from time to time. Okay, so this gives us a better idea, usually. There are some important things in here. So second is, the symbol for second is S, and it is not SN. Kilogram meters squared per second squared, sorry, thanks. So the unit for seconds is not SN, all right? Just keep this in mind. We are using the SI system, so therefore we don't change the name of the units, the shortened name of the units with the culture, with your language, all right? So a German is not using their I don't know Germanic names for these shortened forms. So these shortened forms are actually strict. So let's say it like this: units named after people. Okay, let's say it like this. In that case, the short form is capitalized. Okay, long form is not. It's kind of a strange convention. I don't know why they have adopted this, but it's like that. So the energy unit, for example, joule, it is named after a person. So Prescott Joule, I forgot his first name. He's the person who actually formulated the first law of thermodynamics, which is the conservation of energy principle. He has done important experiments in there, all right? So we know Newton, for example, all right? Or we have Watts, okay? In any case, so all the short forms will be capitalized, but somehow the names of the long name of the unit is not capitalized. And the reason is that probably is that this is the name of the unit. It's not the name of the person. We're not writing the name of the person in here. It's the name of the unit, all right? But somehow the shortened form is capitalized, okay? Apart from that, if the unit is not named after people, right? Let's say all other units, let's say short form is not capitalized, okay? Except these prefixes, which are always written with capital letters like mega and giga and things like that, okay? Yeah, Tesla is an example. There are lots of units, ohms, for example. We use capital omega there. There are many examples from electromagnetism. So most of these units are actually named after a person. The short form is not capitalized, as well as the long form too, and long form too. Okay, so it is meter and the grams and whatever. So the meter and this is gram and things like that. There's an exception. There's an exception to that rule. This is liter. And the reason is that, I mean, this is a symbol that's used a lot on the products like milk, for example. When they write a short L, they cannot write the L because, I mean, even in old typewriters, they have this kind of a confusion. The L letter, lowercase L letter looks like the number 1. And so as a result, there's a lot of confusion arising. And so because of that reason, they then adopted this exception in here that the liter should be written with a capital L, right? So these are the only things that you need to know. And the fact that, of course, always try to use the SI units. Because this is basically our language and the units are maintained, so therefore they are defined in a very precise way, okay? I don't know if you have any questions in here. I don't want to, yeah, I want to say one more thing. So what's important in here is that these kind of equations are meaningful together with a unit, right? So as a result, this equation is meaningful, for example. I mean, think of it as a mathematical equation. It is 1 meter is equal to 100 centimeters, but 1 is not equal to 100, right? Even though we are using different numbers, different mathematical entities as numbers in there, since there are also these units which are multiplied with these numbers, this is a perfectly valid equality. This is valid, but the numbers are not equal to each other, okay? So the lesson in here is, the first lesson is always write the unit when reporting quantities. There are many reasons for that. So there is no fixed convention when we are using units. So even when we are using SI, I can express a length in terms of meters or centimeters or kilometers. It just depends, right? It just depends on what I'm reporting and what is the size of the quantity usually. So as a result, you cannot assume that everybody is using the same unit, right? So when you're reporting quantities, always write the unit as well. And the second thing is, of course, it is only correct with when you write down the unit. So as a result, the convention in here nowadays in science is that if you miss the unit, then this is a mistake. And also in the exams, I usually treat it like that. A lot of us, a lot of instructors actually are treating this as a mistake if you forget about what the unit is, right? So you say that your height is 180, so that's a mistake then. Yeah, let me say it like this, my height. Okay, so that's a mistake because there's no unit written in here, but probably everybody can guess what the unit should be, but we still treat this as a mistake, okay? So that's wrong then. And yes, when we were doing these exams in the classical style, I would actually flag this as a mistake, and I always take 1 point off from these kind of answers. But nowadays we are doing online exams. At some point, I actually asked you to write the units inside the answers that you're providing. I think this actually created a lot of problems for me too. So as a result, in the homeworks and in the midterms, in the online exams, I will always be writing down the units for you. So I'll just ask you to write down the values, the numerical value of the quantities. But if we do the final exam in class, I will ask you to write down the unit in all the quantities, all right? So don't make these kind of mistakes. At least for the final, this is just an important advice. Another thing in here is that the, I don't know, let's say it like this. So let's just take some kind of a formula like this. It's the weight formula. We will talk about these kind of quantities in here. So that's the, let's say, weight formula. It's the weight of an object of, I don't know, the mass given like that. So in a formula, all right, we are basically relating quantities in here. So as a result, when we inserting the quantities in here, let's say, I don't know, mass is 100 kilograms, for example. When I insert in the quantities in here, the units come with themselves, right? And so gravity in here, for example, is 9.8 meters per second squared, right? They always come together with the units. And so as a result, together with these units, this is a correct formula, right? But some people, they just, I mean, especially after in the exams, we insist on writing the units. They always add this additional units in here. So they know that, for example, the weight should be measured in newtons. So as a result, they add a capital N at the end of this, this formula, right? This is wrong, right? It's I mean, you cannot add formulas. You cannot add units to a formula. Okay, so I'm going to give a break in here, but let me explain why. Because this is dimensionally incorrect, right? Because if you just insert in these values in here, in that case, the mass would be 100 kilograms. So there's already a kilogram in here. Gravity in here is 9.8 meters per second squared. And somebody else has written an extra unit in here. So the result would be like 980 Newton multiplied with kilogram meters per second squared. And you notice that this is basically the Newton unit. So that's Newton unit. So it appears that the quantity W has the unit of Newton squared. So therefore, this is an incorrect unit. Okay. This is wrong because there's already a Newton in that expression in here, right? The unit is already within the formula. So as a result, you cannot write down, you cannot add units to a formula. This is wrong. This is correct, right? So when you insert in the values in here, you are going to get the correct expression in here. So I don't know, let's say it like this. You're going to think that this is a very stupid exercise. But for example, I can compute the weight correctly if I insert in, for example, different units in here. So it is in, let's say, in these units, the weight will appear to be 980 kilogram meter per second squared. So therefore, this is 980 newtons. Or I can use the same formula, but this time I can use the grams instead of kilograms. And I can use perhaps centimeters in here instead of meters, right? It's the same quantity basically. So that quantity and that quantity is the same. So I'm inserting the same value in here, but there's a different numerical value, right? In this case, what I'm going to get is 9.8 times 10 to the, 5 and 7 in here. And the unit is grams centimeters per second squared. We know that the unit is dynes, right? So therefore, this is this much dynes. And I know that 10 to the 5 dynes is equal to 1 Newton. And so therefore, this is the same thing as 980 Newtons in here. Okay. So in any case, the lesson in here is that I could have used the same formula to compute the weight in a different unit. Nobody forces to actually express, nobody forces me to express the weight in Newton units. There's some kind of a freedom I have. So it's just the quantities in here. So I have the mass quantity in here and the gravity quantity in here. I can express this quantity in any way I want. I can use kilograms or grams or tons or whatever. That's up to me, all right? So as a result, I mean, this kind of a form is actually consistent with this choice in here. And whatever your choice is, you always get the same quantity, right? Same value together with the correct unit. And so as a result, this, I mean, at the end, this is the summary, all right? When you're writing formulas, write the formula without any units. Okay, I'm going to add one more thing in here, but let's take a break. After the break, I'll just say this and then continue with the rest. Okay, so let me stop the recording first. Stop recording.